Our next topic to consider is air with a little bit of water vapor mixed in with it, so humidity. If you think about dry air, the main things that it contains are nitrogen and oxygen. In this little air parcel graph that you see here, there are nitrogen molecules indicated by the green diatomic molecules bouncing around due to their thermal energy. And there are oxygen molecules, also a diatomic molecule, that's in red, zipping around also because it has thermal energy. So this is just gas. Those are the two primary components, of course, that make up air. There are other trace gases as well, but we're not interested in that right now. In fact, this picture is not all that precise or accurate yet because you notice that there, if you count the number of oxygen molecules, they're about as many, if not more, than the number of nitrogen molecules. In reality, the air that we breathe consists of primarily nitrogen. I think, 21% oxygen? So the other thing that's not accurate is you'll notice there are some other, almost look like Mickey Mouse molecules. They're red, indicating an oxygen, and then two white spheres on them indicating that these are water vapor, so H2O, 2 parts hydrogen, 1 part oxygen. Also in the gas phase, zipping around with it. And then again, there's too many of them, right? The main thing we should see is a bunch of green diatomic nitrogen, quite a bit of diatomic oxygen, and then very small amounts of water vapor. But you get the idea. All these things are mixed together and bouncing around. So we're not dealing with a substance that is a single chemical component. We're dealing with something where the dry air itself is present, but then there's some water vapor mixed in. And it's really important to get this concept of dry air, because when we say dry air, we're not talking about the air and saying that there's no water vapor in it. We're saying the section of the air except for the water vapor. So imagine that the water vapor is not there. That air is the dry air. That's why we call it the dry air. So the air without the water. And then there's some water vapor mixed in with that dry air. Now, why would we make a distinction between those? Well, the amount of water vapor in the air will vary quite a lot in the problems we're looking at. In fact, there are a lot of engineering systems whose sole purpose is to change the amount of water vapor in the air. You probably have a humidifier at home, or if not, you probably have an air conditioner, which is actually a dehumidifier. At least in our area of the country, here in the Ohio Valley, the air conditioner in the summertime does two main things. One thing is to cool down the air in your home, the temperature, but another huge application of air conditioning is actually to remove a significant quantity of water from the air. It makes the air in your home or your office feel much more comfortable. So in order to analyze these, we have to make a distinction between the dry air portion and the water vapor, where the quantity of, just think of it as the number of molecules, is going to be going up and down, depending on what kind of system we're looking at and what we're doing with it. Now, in order to track what's going on here, we will have to keep track of energy, and in particular, the enthalpy of these various gases will be quite interesting. So the dry air itself, the nitrogen and oxygen mixture, we can estimate its enthalpy by the equation, its heat capacity at constant pressure times its temperature will give us an estimate for its enthalpy. And we're really not interested most of the time in absolute values of enthalpy of the dry air portion. What we're really interested in is changes in the enthalpy of that dry air. And so what you'll notice is that the next equation is really the one we'll pay more attention to. It says that the enthalpy change of the dry air is the heat capacity of the air times the change in temperature of that air. So that's great for the air, and you could have written that down by this point in the course already. But what about the water vapor? It's going to have enthalpy also, right? It has some thermal energy. And so how will we approximate it? Well, what if we imagine it as an ideal gas? Now, what are the tenets of an ideal gas? Well, one of the tenets is that the gas takes up no space. Well, that's reasonable. The amount of space taken up by the water vapor itself in a volume is actually very small. The air itself doesn't take up much space. The molecules themselves, right? I mean, the air in everyday life, which is most of the time what we're interested in, is atmospheric conditions. Most of the time, the amount of space taken up by the gas molecules, whether it's nitrogen, oxygen, or water, that's in the air, it takes up a small amount. So it's not unreasonable to say that the water vapor is acting as an ideal gas from that standpoint. What else is there? The other thing we assume about ideal gases is that the gas molecules don't interact with each other hardly ever. And since, again, they're spread out, they typically don't bounce off of each other by comparison to their motion. They do, of course, occasionally, but by comparison, it's not like there's a bunch of traffic collisions in one small area per unit time by comparison to how many there could be. So treating the water vapor as an ideal gas is really not that bad, assuming that the water vapor is away from its critical point. And if you remember when we studied a compressibility factor, we found that actually water vapor does behave as an ideal gas in a significant region of temperatures and pressures. And so if we look at a TS diagram for water vapor, what you'll notice is that at relatively low temperatures and relatively low pressures, the enthalpy of the water vapor is constant. And look at the schematic I've got here of a TS diagram of water. Below 50 degrees Celsius or so, notice that the lines on the right side that are constant enthalpy lines, or isenthalpic lines, are basically just horizontal. And what that really means is that the enthalpy doesn't change with entropy. It just depends on temperature, right? So it does change with temperature, but beyond that, the enthalpy is pretty much constant regardless of its entropy. And so we can approximate the enthalpy of the water vapor as an enthalpy that depends only on temperature. And the key here is that that enthalpy value is the enthalpy of saturated vapor. So we can take that line regardless of how far out it is. We can take it all the way back to the vapor dome and look up the enthalpy of the water vapor simply as a function of temperature in the saturated tables. Now, it really shouldn't be a surprise that the enthalpy of the water vapor is only a function of temperature, given that the water is behaving as an ideal gas. Remember, ideal gases, their internal energy and their enthalpy depends only on temperature. Now, it's very convenient, of course, that the particular enthalpy we can use is the enthalpy of the saturation value. That's quite useful. Here's an actual TS diagram for water vapor. It's in your text. If you look close on the right-hand side, you will see isenthalpic lines. I'll leave it to you to look it up in your textbook and verify what I've said, that below about 50 degrees Celsius or so, which is the Y temperature axis, to the right of the vapor dome in the superheated region, the lines are pretty much just horizontal. And so we can take the enthalpy to be the enthalpy of saturated vapor at whatever temperature we happen to be. So now we finally have a way to find the enthalpy of the water vapor. It's a little bit difficult to always have to go back to the back of the book and look up the enthalpy. As a matter of fact, you have to interpolate so often. It's useful to instead have an equation that would allow us to plug in a temperature and get out the enthalpy. That way we don't have to look it up so much. And so here are two equations for you, both of them from the text, of course, one for metric units and the other one for English. And they're just inconvenient units. In other words, the temperatures for the metric version are in Celsius, and for the English version they're in Fahrenheit. Now, this is the one time that you'll see equations where we use temperature on its own and we don't have to convert to absolute units. It's one of the very rare times. And the reason is that these are just curve fit equations. These are just based on convenient units. You know, it's a line fit, kind of like you would do in statistics, least squares fit. If you go and you look up the enthalpy as a function of temperature in the saturated tables and then compare that to what these equations give you, you'll find that there is a difference, but it's quite small. So here's an analysis of the amount of error reading the enthalpy off of a table given the temperature versus using the equation that's there on the left. Of course, it would be the upper equation, and how much difference there is. And the difference is very, very small. So these equations are quite useful for that purpose. Finally, now we get to humidity. So we can define, or we can quantify the enthalpy of the air itself, and we can quantify the enthalpy of the water vapor that's in the air. But what about how much water vapor is in the air? Well, that's what we use the absolute humidity for. So the absolute humidity is very simple. It's just defined as the mass of water vapor in a given volume of air divided by the mass of the air itself without the water vapor. Now, obviously, the air is mixed in with the water vapor. There's no magic way to grab a hold of it and pull it separate from the water vapor. But the point is, we're looking at the ratio of the mass of the water vapor to the mass of the air itself. Now, you might say, well, that seems okay, but why wouldn't we use the mass of the water vapor plus the air as the denominator in the absolute humidity? Well, the problem with that is if we start playing around with the amount of humidity, removing and adding water vapor to the air, we'll change the mass. And our reference in the denominator, we'd like to just have constant. So we use the dry air itself as our reference mass, so that we can talk about this this fraction. Really, what it is a mass fraction. Though a little different because it's a mass fraction based on a portion of the mass in the mixture. But anyway, now if you think about pressure, you should realize by now that pressure is really just a side effect of the thermal motion of the gas. That's all it really is. And so it's really pressure is generated from molecules bouncing off of surfaces. And so if you think about what's going on in air that's humid, there's of course the dry air portion, which is the nitrogen and the oxygen, and then there's the water vapor itself. Both of those components bounce off whatever container they're in or whatever surfaces they encounter and generate pressure. So the total pressure being generated is simply the sum of the pressure generated by the air and the water vapor. And so we call these pressures PA, the pressure generated by the air, and PV, the pressure generated by the water vapor, thus the V. We call those partial pressures. So it's the part of the pressure that's due to that particular component in the mixture. So with this information and with the fact that we can treat both the air and the water vapor as ideal gases, we can now take our absolute humidity ratio or specific humidity, and we can replace the masses of the water vapor with the ideal gas equation for the water vapor itself and the mass of the air with the ideal gas equation for the air. Now notice that in the pressures we're using the partial pressures of each of those components. Okay? Now, since both species take up the entire volume and bounce around in the entire, imagine it as just a box or a container or your room, for example, well then they take up the same volume, so the volume cancels. In fact, they're in thermal equilibrium, and so they have the same temperature. So we could cancel both the volume and the temperature out of both ideal gas equations. Since the gas constant for water vapor and the gas constant for air are themselves just constants, we can take the ratio RA, the gas constant of air, over the gas constant for the water vapor. That comes out to 0.622. The units cancel, of course, and we can simplify the equation. So this is a very convenient way to write the absolute humidity and quantify the amount of water vapor in the air based on the partial pressures of the water vapor and the air. And a lot of times what we'll do is, if we know the partial pressure of the water vapor itself, we'll just take the total pressure minus the partial pressure of the water vapor to represent the partial pressure of the air, make the substitution, and here we go. So now we've got an expression for the absolute humidity based on the total pressure in the container and the partial pressure of just the water vapor. Relative humidity is a little bit different. If you listen to a weather report and they tell you the humidity is a certain thing, it'll be a certain percentage. They don't give you the absolute humidity. Absolute humidity numbers are usually fairly low, like 0.01 something. Okay, on that order is the absolute humidity. In other words, the mass of water vapor in the air is usually about 1% or so. So they usually give you a relative humidity, which is defined as the mass of water vapor in a given volume of air divided by the maximum amount of water vapor that could be in the air. Now, if you think about what's going on, if the air and the water vapor don't really interact with each other, then it's almost like they don't know the other one's present. So it's almost like the water vapor is behaving as if there were no air around it, right? It's just in a container, and it's behaving as it would in that container. Now remember, if we have too much or too high a specific volume of the water vapor, we can get into the saturation region, right? In other words, we can start to have some of it condense out. So that's what we're looking at here. If the partial pressure of the water vapor is less than the saturation pressure, okay, then the air is said to be unsaturated. It's not really the air that's saturated. A lot of people use an analogy here saying you can think of the air as like a sponge that's soaking up water and it's full of water. But the thing is that the water doesn't know the sponge is there in that analogy. All the water vapor knows is that it's water vapor, and it behaves in accordance with saturation measurements that we made of them, of water vapor. It's very consistent. So if the partial pressure of the water vapor goes all the way up to the saturation pressure for the whatever temperature it happens to be at, and you see here we're talking about air at 25 degrees Celsius, 100 kilopascals, the saturation pressure for water from the saturated tables at 25 degrees is 3.1698 kilopascals. If the partial pressure of the water vapor gets up to that level, then that means we're on the verge of some of that water condensing out and converting to a liquid. Now, since we can write the ideal gas law for both the mass of the water vapor that's actually in the air and the maximum amount that could be in the air, notice we're using PV, the partial pressure of the water vapor that's actually in the air, for the mass of the water vapor, and for the mass at saturation we're using the partial pressure at saturation, PG. Well, they all take up the same volume, they're at the same temperature, and the gas constant is the same because both are water vapor now. We're not talking about, you know, water vapor over air, for example. We're talking about just water vapor at, you know, current conditions versus saturation conditions. In that case, it's just the ratio of the partial pressure of the water vapor that actually is in the air divided by the saturation pressure at whatever the temperature happens to be. So that pressure there, that partial pressure at saturation, you just look up based on the temperature. Like, for example, I gave you air here at 25 degrees. Well, just look up the saturation pressure of water vapor at 25 degrees, and that's what you plug into the denominator here. Now, there is a relationship between absolute and relative humidities. If you think about it, we can put these two together, and it's pretty easy to see. We could just write the relative humidity phi multiplied by the saturation pressure P sub G, that would be the partial pressure of the water vapor PV, and substitute that into the equation for the absolute humidity. If you do that, you end up with an expression that relates the absolute humidity omega to the relative humidity phi, and you can of course rearrange it to write the relative humidity phi in terms of the absolute humidity omega. So these equations are not independent, they are the same equation. Alright, so what about the enthalpy of atmospheric air? Well, the enthalpy of the air itself is going to be simply the sum of the enthalpy of the air plus the enthalpy of the water vapor. Now, we like to think about this air, a parcel or mass or whatever in the container, we like to think of it as the air by itself with the moisture by itself. Really, they're mixed together, right? Really, there's 1 plus omega kilograms of moist air, that's the total mass here, for that 1 kilogram of dry air, because we've got omega kilograms of moisture, where omega, of course, is the absolute humidity. Now, the amount of enthalpy in this mixture is going to be the mass of the dry air times the enthalpy that air has, HA, plus the mass of the water vapor times the enthalpy that it has. I started off with total enthalpy. If we want to talk about enthalpy per unit mass, which we usually do, the question becomes, what mass do we take? Do we take 1 plus omega as the mass, the reference mass? Well, the problem again with that is that the amount of moisture is going to change, and so we'd rather take the dry air itself as our basis. So our specific enthalpy by definition is the total enthalpy of the mixture divided by just the mass of the dry air. The specific enthalpy will simply be the enthalpy of the air itself plus the ratio of the mass of the water vapor divided by the mass of the air times the enthalpy of the water vapor itself. Okay? Now, of course, that ratio has already been defined. The mass of the water vapor divided by the mass of the dry air is what we called the absolute humidity. Now, if you understand all that, great. Here's what you need to know. The specific enthalpy, the enthalpy per unit mass, is taken with respect to just the dry air mass. And it's simply equal to the enthalpy of the air plus not the enthalpy of the water vapor, but the enthalpy of the water vapor multiplied by the specific humidity. You know, if you wear glasses, you've probably experienced your glasses fogging. We've probably all experienced our windshields on our cars condensing over. You've probably drank a cold soda and noticed the side of the can sweats, and you might feel like, well, does that mean there's leakage, that some of the liquid is somehow sneaking through the aluminum and coming on the outside? Well, of course, that's not the case. Actually, what's happening is the air around the can is being cooled. It has some water vapor in it, and that water vapor then condenses out onto the can. And so what happens when water condenses out of air onto a surface is that that surface must be at a low enough temperature called the dew point temperature in order for dew, and by the way, dew is D-E-W, and you pronounce it like you do D-U-E, dew. Anyway, there is a dew point temperature, and notice that the partial pressure of the water vapor in the air is a constant, right? I mean, as long as there's a certain amount of mass in the air, the partial pressure will be constant. As the temperature goes down, therefore, the water vapor is moving along a line of constant pressure. Again, it doesn't know that there's any air around at all. It's behaving as an ideal gas. And eventually we'll go from state one, the temperature outdoors or wherever it happens to be, down to what's called the dew point temperature. And of course, that dew point temperature is the temperature that's on the saturation line. So this is why dew forms on all sorts of things. It's simply that those surfaces are cold enough that they're either at or below the dew point temperature, and so the water vapor in the air in the immediate vicinity of the can simply condenses out on the soda can. So how do we measure humidity? Well, there's a couple of different ways to do it, but the easiest way to understand, to start our discussion, is to imagine a very long channel where we have some liquid water in this channel. And what we're going to do is run air that is unsaturated. In other words, it has some water vapor in it, but it's not completely full of water vapor. It's not at the saturation point. We're going to run this air through this chamber in order to let some of the liquid water evaporate off and go into the gas phase. Now, what's happening is the partial pressure of the water vapor in that air, which is, of course, the air that we're testing coming in at state one, the partial pressure of the water vapor in that air is actually going to go up. So this process will not follow a constant partial pressure line, as you see on the TS diagram. Rather, the partial pressure of the water vapor will be increasing because the water is evaporating off into the air and saturating the air, or the partial pressure of the water vapor is coming up to the saturation pressure, P sub G. Now, what will happen in this process, since it takes energy in order to get the liquid water to evaporate into the vapor phase, that energy has to come from somewhere. It can't be created or destroyed. So it comes from the air and the water vapor already in the air, giving up energy in order to evaporate more water into the air. And so the temperature of the mix comes down. And so the exiting temperature at state 2, T2, will be lower than T1. And of course, the air will be at 100% humidity if we make this channel long enough. Let's just assume that we do, and we have adequate design to ensure saturation at the exit conditions. Now, the curve that's being followed from state 1 to state 2 on the TS diagram is what's called an adiabatic curve, and the temperature it reaches is the adiabatic saturation temperature. All right, so let's think about the air. Well, if this is operated at steady state, then the mass flow rate of the air coming in at state 1 and the mass flow rate of the air leaving at state 2 are the same. We could simply call it the mass flow rate of the air. The water, on the other hand, some water enters at state 1, but more is added from the liquid that evaporates. And then more mass, therefore, leaves at state 2 of water vapor than entered at state 1. Now, of course, the mass flow rate of the water coming in can be written in terms of the mass flow rate of the air simply by using the absolute humidity coming in at state 1, omega 1. The mass flow rate of the water leaving, which is, of course, vapor at state 2, it can be written also in terms of the mass flow rate of the air using the absolute humidity at the exit. And m dot sub f is simply the mass flow rate of the liquid water that's evaporating into the air. So the mass flow rate of that water that's evaporating and adding to the airstream can be written in terms of the change in absolute humidity through this device. Now, we also have to write an energy balance in order to get anything useful out of this analysis. And so let's think about the amount of energy and where it comes from. So some of the energy comes in at state 1, right? The air that comes in carries enthalpy in both the air and the water vapor, and all of that is captured in H1. The liquid water also brings in energy. HF2 there is just the enthalpy of saturated liquid at T2, because that's the temperature of the liquid water. And then the enthalpy of the exiting humid air is just the mass flow rate of the air times the enthalpy at the exit. Again, H2 contains both the contribution from the air and the contribution to the enthalpy from the water vapor. Now, from the mass balance on the water, we can substitute for the mass flow rate of the makeup water or the added water, as you can see there in the slides. And notice that the mass flow rate of the air cancels out of the energy balance, and that's a nice, handy thing. Now, if we go back to our equations that allow us to quantify the enthalpy of the air separate from the enthalpy of the water vapor, you'll remember that we use CPT in order to do that. And so for the air, you see CPT1 and CPT2 in the equation representing the enthalpy of the air, and then omega 1 Hg1 and omega 2 Hg2, the enthalpy of saturated vapor, water vapor, representing the enthalpy of the water contribution, the water vapor contribution. And so from this we can solve for the absolute humidity in state 1. Now this looks like a mess. It looks like, well, we've not really done anything interesting, but wait a second, yes we have. The temperature at the entrance and exit are easy to measure, right? We can just stick thermometers there. All we need is the absolute humidity at state 2, but we know that the relative humidity is 100%, and we know a relationship between relative and absolute humidities. We need the enthalpy of saturated water vapor, both in the liquid and vapor states for T2, but we can look that up in the back of your text. And we need the enthalpy of saturated vapor coming in, but that again is a lookup based on T1, and we need the enthalpy of the saturated liquid at T2, another lookup. So since we can substitute for the absolute humidity based on things we know, we can actually calculate the incoming absolute humidity based on things we can measure. Now this is not the only way that this can be measured. Another way to do this that's a simpler setup is to use a so-called wet bulb thermometer. So we use an ordinary thermometer, but on it we put a wick, and we allow liquid to be drawn up by the wick while we blow air across it. And what will happen is the air blowing across will absorb it'll pass through the wick, and it'll absorb water vapor, becoming saturated. Now what will end up happening is the wet bulb temperature, or the wet bulb thermometer now, will drop its temperature just like the channel did, where the exiting state, state 2, was fully saturated. And if we blow the air hard enough, we get enough water in there, we can saturate the air as it goes by. Now, one pass probably won't do, so what's used to make this practical is something called a sling sacrameter. And if you look at this device, you'll notice that it has what's called a dry bulb thermometer and a wet bulb thermometer. Now, don't be put off by all the different temperatures we're going to have. The so-called dry bulb temperature is just the temperature you're used to talking about. So far in any class, most likely, if you've talked about temperature, you were talking about dry bulb temperature, just a regular thermometer, regular measurement. We have to have that distinction now, though, because now we can put a wick and some type of moisture source onto the end of the wet bulb thermometer, and thereby cool down the wet bulb thermometer as air flows across it. Now you might look at this and say, well, I don't see any airflow for this so-called sling sacrameter. How do you do that? Well, that's where the slinging comes in. You actually grab a hold of the handle that's sort of horizontal there, and you sling it around above your head or beside you, and what happens is that's what generates the airflow across the wet bulb so that the temperature of the wet bulb thermometer drops. And by looking at the dry bulb and wet bulb temperatures, you can then go back to the equation that we had a moment ago and figure out the absolute humidity of the air under test. Now, all of those equations for relating temperatures and enthalpies and absolute humidities and relative humidities, they're useful, they're nice, but it's very inconvenient to have to go through them and use them every time. Instead, what's used most often is what's called a sacrametric chart. And here's a reprint from your text of the sacrametric chart. There's one for English units and there's one for metric units. I like the English unit chart simply because the absolute humidity numbers are given as absolute humidity, whereas in this chart, which is the SI chart, the absolute humidity numbers are a little different. If you look on the right-hand side, you see the 30, 28, 26, 24, all the way down to 2. Those are the absolute humidity numbers. That's the absolute humidity scale. And those numbers, to get the actual fraction, you have to divide it by 1,000. In other words, this is showing you grams of water vapor over kilograms of dry air. And you'll notice that it's a rotated text, and there's a little note there saying humidity ratio omega is grams of moisture per kilogram of dry air. But if you forget that, it looks like you got, say you're at 20, it looks like you got 20 times the amount of mass of water as you have air. Well, if that was the case and you're breathing it, you'd be dead, you'd drown, right? So obviously these numbers are not what they would appear at first glance. They are rather grams per kilogram rather than, say, gram per gram or kilogram per kilogram. On the English table, you might go look at that in your book now, and by the way, these are 2 pages well worth marking in your book. You might notice that they have like 0.02 or 0.01, etc. Now, one thing about this chart is it's only good for one pressure. As the pressure changes, the shape of the chart changes slightly. And so as long as the pressure is reasonably close to atmospheric pressure, 101.325 kilopascals or 14.7 psia, you can use the chart and get away with it. Even if you're, a couple tenths of a psi off, it'll still be close enough. But if you're anywhere, down to say 5 psi or up at 50 psi or something, and you have some kind of process, an enclosed vessel with air and water vapor in it, then you can't use these charts. You have to use either a sacrametric chart that's generated online, and I've provided some links for that also, where you can input the pressure and it generates a custom sacrametric chart, or you have to go back to the equations and use those instead. Now let's study this chart a little bit. Here's a schematic of the chart showing the relevant data and how it's plotted. And you'll notice that the x-axis down at the bottom is the so-called dry bulb temperature. That's just the regular temperature you're used to measuring. And I've already pointed out the specific humidity or the absolute humidity on the y-axis on the right-hand side of the chart. So take a moment and look at those numbers. Make sure you know where they are. So the dry bulb temperature is 0, 10, 20, all the way up to 50 on the x-axis, and then absolute humidity 2, 4, 6, all the way up to 30 on the what would be the y-axis on the right-hand side. The other lines on this, one of the really important lines is the saturation line. Now, if you'll notice on the upper left side of the chart, there's a straight line. Don't look at that. That's not really part of the chart. You can read off there, but that's for your convenience. The saturation line is actually that last curved purplish line, pink or purplish line, whatever it looks like to you. And that saturation line is as far as the water vapor and air mixture can actually go. There's the water vapor and air mixture is going to exist in some state represented by a particular point on this diagram. And those points can only be inside of the region that I guess kind of looks like a shoe or a boot or something with the toe on the left. But it's definitely curved, and the mixture can't go past that curve. So the saturation line is the line where there is as much water vapor in the air as possible. No more can enter the air because the partial pressure of the water vapor is at the saturation pressure for that temperature. And so what you'll notice next is that curved line then all the way on the left must be the line for 100% relative humidity. Now as you move down, unfortunately my figure's blocking right now, but you see the next curved line is labeled 90%. Well, the one after that is 80%, 70%, and so forth, where the last curve is labeled 10%. Of course, you can't see it from my inset here. Now, the lines of constant specific volume are almost vertical. Well, not really. They're still slanted to the left a bit, but you'll see those, for example, on this chart, they're labeled 0.78, 0.8, 0.82, 0.84. I can't see the others until we get to the other side of my inset, and the only one I see there is 0.92 and 0.94. Now, what about the lines that are not labeled? Well, it's just the number between. For example, 0.78 to 0.8, that line between that's not labeled is just 0.79. And the units there are, let's see, it's labeled on the 0.92 line to the right of my inset. It's volume in cubic meters per kilogram of dry air. So again, all of this is referenced to kilograms of dry air. Without the inset, it's easier to see the next couple of lines. There are a set of lines that are different things, but that almost lay on top of each other. Do you see the solid black lines that run sort of downhill on a slight slope? And then there are some dotted lines that run almost parallel to those. Well, the dotted lines are lines of constant wet bulb temperature. And so you'll notice there's one that's labeled, it's 25 wet bulb temperature in degrees Celsius. And if you go up, let's see, you can tell that that goes with a dotted line. If you go up, let's see, 1, 2, 3 black lines, you'll notice there's a dotted line very close to that black line labeled 30. It's really confusing because that 30 does not go with the dark black line. It goes with a dotted line. And it's kind of hard to remember that until you get used to it. But going down from the 25, you'll see 20 on a dotted line, and the next one's 15. It's clear that's with a dotted line. But then you get down to 10, and it breaks a solid black line again. So does the 5, and then the 0 almost looks like it does as well. Unfortunately, the sets of lines, although they're different things, are so close to one another, it's difficult to distinguish. Those numbers I've just pointed out, 0, 5, 10, 15, 20, all the way up to 30, those numbers go with the dotted lines. The dotted lines, as I said, are lines of constant wet bulb temperature. The solid lines, on the other hand, are the enthalpy of the air and water vapor mixture. So they are lines of constant enthalpy. Now that's what the straight scale is on the left-hand side of this diagram. It's a scale for the enthalpy in kilojoules per kilogram of the dry air itself. Again, the basis is the dry air without the water vapor in it. One interesting thing about this, you'll notice that these solid black lines, they go all the way across, and if you look on the vertical axis on the right, you'll notice that there are labels on that side for the enthalpy going from 120, 110 all the way down to 60, and then at 50 it turns the corner, and you might notice that the lines of constant enthalpy numerically go almost exactly through the lines on the horizontal axis. And the horizontal axis lines, though, those are temperatures. So why on earth would the temperature lines almost match the enthalpy? That doesn't seem to make sense. The reason for it is because the heat capacity that we're using for the air is about 1.005. It's very close to 1, right? So at relatively low temperatures, that heat capacity times the temperature in Celsius is going to give rise to an enthalpy that's numerically almost equivalent. There's just a 0.005 that means there's a little more. So like 10, for example, would be what? 10.05 kilojoules per kilogram, representing the enthalpy of the dry air. And notice that bottom horizontal line would represent 0 humidity, right? So no water in the air. And so that it makes sense if you stop and think about it, why the solid black lines that represent enthalpy would almost look like they have a reading on the horizontal axis when really the horizontal axis is temperature. It's just a side effect of the way that we're quantifying the enthalpy of the dry air itself. Now, if you have a state that's on the saturation line, then all of the temperatures are the same. So, for example, if you have a dry bulb temperature of 15 degrees from a sling sacrometer and a wet bulb temperature of 15 degrees, then either you've not wetted the wick on the sling sacrometer, or if you did wet it and you've slung it for quite a while, that means the air in the room, or wherever you're slinging it, is completely saturated with water vapor. It probably feels pretty muggy in the room to you. Anyway, at that point, the wet bulb temperature, the dry bulb temperature, and the dew point temperature will all be exactly the same and represent the state of the water vapor air mixture on the saturation line. But more generally, most of the time what you'll find is that the state is a particular point within the body of the diagram, and from that point you can read off the enthalpy, the wet bulb temperature, the dry bulb temperature, the absolute humidity, anything you want to know there. So knowing any two of these, say you know, I don't know, let's say you know the dry bulb temperature and you know the wet bulb temperature, okay? Well, draw a line from the dry bulb temperature up just vertically, okay, it'll just be a vertical line, and then take a line from the saturation line, getting the wet bulb temperature, and following a wet bulb curve down. Wherever that intersects the vertical line from the dry bulb temperature, that's the state of the humid air. And from that point, you can just go off horizontally to the right, read off the absolute humidity, go to the left, read off the dew point temperature, and whatever curved line you happen to fall on, that's the relative humidity. And of course, you can go up the dotted line and read off the enthalpy of the water vapor and air mixture. So this is a very handy chart because you don't have to go through so many equations to find out the properties of the gas at the given state.